Welcome to this session. In this session, we will be focusing on constraint optimization. In this particular session, we will be focusing on introducing the problem and the optimality conditions. The content of this particular session is we will start with the introduction. Thereafter, we will discuss the optimality condition for unconstrained optimization. Followed that, we will be discussing the method of multiplier for constraint optimization. This method of multiplier, we will take it further. We will understand the KKT condition for constraint optimization. And finally, we will conclude this session. So, let us begin with the introduction on constraint optimization. Now, as we can see here, a constraint optimization problem can be written as minimization of the function f(x), and this particular problem is subjected to inequality constraint, which is represented as Gj of x, and the total number of such inequality constraint we can have capital J. Similarly, we can have equality constraint and we can have multiple equality constraint, which is represented by capital K. Apart from that, the problem can have the variable bounds. So, as we can see in equation number 1, we are minimizing a function which is subjected to inequality constraints, equality constraints and the variable bound. Now, here the x which we are writing, that is a column vector for us. So, this is a vector for a decision variables, and as we have understood that since we are minimizing the function, so f(x) is our objective function and Gj of x is our inequality constraint and Hk of x is the equality constraint. Here, when we are looking for a solution, as and when a solution satisfying all the constraints including the variable bound, this particular solution is referred as feasible solution. And as and when any solution which is not satisfying a single constraint or more than one constraint or the variable bound, that solution is referred as infeasible solution. So, from this discussion, we can find that one particular constraint or a group of constraints can make some solutions feasible and some solutions infeasible. So, as we have mentioned here, it means that, so basically because of the constraints, these constraints can restrict solutions to be feasible. So, we can divide a set of solutions into feasible and infeasible solutions. There are various kind of constraints. Now, let us see that. We can have constraint like linear equations or we can have non-linear equations. Inside these two categories, we can have equality constraint as we have shown in the previous slide, and we can have inequality constraints. Under non-linear constraints as well, we can have equality and inequality constraints. So, these are the different types of constraints we can have in an optimization problem. Generally, it is found that the linear constraints are relatively easy to handle with. However, the non-linear constraints can be hard to handle. So, it is a relative term. So, we found that from the various simulations, linear constraints are easy to handle. Now, let us see what kind of examples or constraint optimization methods we can have. So, instead of a methods, we should say constraint optimization problem. So, the first graphical example is shown for box constraint, meaning that the feasible search space is defined by the bounds on the variables. So, as you can see in this picture, we can have this lower bound on x1. Similarly, I can have upper bound on x1. Similarly, we can have lower bound on x2 and the upper bound on x2. So, these bounds are making this particular region feasible, and when we run any optimization algorithm, we will get this optimal solution, which is represented by the green color. The another problem is that suppose we have, along with the variable bounds, which is you can see on x1 and x2, we can have other constraints. That constraints make this particular feasible space. So, this oval shape is now our feasible space. Now, here what we can see that the optimum solution which we had in the previous slide, that is the same as the optimum solution for this scenario, meaning that the constraints do not change the previous optimal solution. So, in that case we can understand that even if there are constraints into the problem, but the optimum solution remains the same as we have found without those constraints. So, with the help of variable bounds only, we can locate where is the optima. Look at the third situation, which is generally the case that we have one constraint. As you can see here, this particular constraint is making our previous optimum solution. So, that is the red dot here, and this red dot is now infeasible, meaning that the constraint that is introduced right now, that makes our previous solution infeasible. And you can also see that our feasible space is also changed because of this constraint. So, that is why some constraint in the problem can make our previous optimum solution infeasible. And in such kind of a scenario, most of the time we found that the optima solution is generally lying on the boundary of this feasible space. Let us see what could be the search space we can have it. As we can see here, we can either have a continuous search space or we can have a discontinuous search space. Looking at the figure on the left hand side, this particular space is made by the constraints as well as the variable bound. So, we have just one feasible space, and that is continuous, as you can see from this left hand side picture. Now, looking on the right hand side, we have a search space S. Inside this, we can have disconnected feasible spaces. Now, from these two figures, we can see that when we are solving a problem which is making a continuous search space, those are relatively easy to solve. But if the problem is making our disconnected search space, those problems are difficult to handle. Now, since we have understood that what could be the constraints, the various types, and those constraints are making some solution feasible, some solution infeasible, as well as those constraints can make the search space continuous or discontinuous. Now, let us move towards the optimality condition. We will begin our discussion on the optimality of unconstrained optimization problem. Now, if I am saying unconstrained, this means that there is no constraint on the problem. We are either minimizing a problem or maximizing it. For our reference, let us take minimization of a function f(x). So, let us look here. So, we will be using the Taylor series expansion for multivariable function. So, the function f of x is a multivariable. As you can see, the x is a column vector here. So, here let us assume that the function, the gradient of the function, and this is gradient of the function, they exist and as well as continuous for all value of x, that is belonging to the real space of n. let us assume that we have x bar, which is a minimum point. We are going to use the Taylor series expansion at a current point, say x bar, and we can write this particular equation as f of x bar plus delta x. We are going to expand using the Taylor series expansion, so we get f of x bar plus gradient of the function at x bar transpose delta x. So this transpose means that we are performing a dot product here. The third term is half of delta x transpose gradient of the function at x bar and delta x plus the other terms. Now here you know that this delta x is also a vector. Now if we are going to rewrite this equation, meaning that the equation number 2, this particular term on the right hand side we are taking into the left hand side. Looking at the equation number 3, we have delta of fx. This is f of x plus delta x minus f of x bar. And then we have the rest of the terms, which is as per the equation number 2. So we have the first term and then the second term, and we have the rest of the terms here. Now since we have assumed we are using a minimization problem here, so we know that for a minimization problem, this delta f of x should be greater than 0. Why? Because we know that this x bar is the minimum point. So whether the delta x value is positive or a negative, the function value of x bar plus delta x will be greater than the function value at x bar. So this says that the delta of f of x should be greater than 0. If we are including this particular condition here, so in equation number 3, so this right hand side should be greater than and equals to 0. While doing so, we have this particular first term which is underlined here, the second term and the third term. Now since we want the right hand side of the equation should be greater than equals to 0, so we know that the dominating term in this particular side is gradient of the function at x bar transpose delta x should be greater than 0. If this dominating term will be greater than or equals to 0, then rest of the terms will be quite smaller as compared to the first term. So in this case, what we will see that if we want the gradient of the function at x bar transpose delta x, if we want this should be greater than 0 for any arbitrary value of x. This means if delta x can take positive value as well as negative value, this condition can only true when we say the gradient of the function at x bar is equals to 0. So this particular condition is known as the necessary condition for the unconstrained optimization problem. So let us take further, and we have to find the other conditions. Now here we have written this expression as delta of f of x, which is f of x bar plus delta x and the function value at x bar. So difference of that is the right hand side which we have found in the previous slide, and everything should be greater than 0. Since for an arbitrary value of a delta x, gradient of the function at x bar should be 0, and let us ignore the other term, we will get the equation number 4, which says that the delta of f of x is equals to the second term, which is half delta x transpose gradient of the function at x bar and delta x, and that should be 0. Now this particular condition is important for us. Why? Because this set of a condition will give us another condition, meaning that we are going to get the sufficient condition for us. If our delta of f of x is greater than equals to 0, that is what we are doing right now in equation number 4. In this case, this gradient of the function at x bar is a positive definite. If this is positive definite, meaning that x bar is the local minimum solution. Similarly, if we use the Taylor series expansion for the maximization problem, what we will see here is that if delta of f of x is smaller than 0 and this gradient of the function at x bar is negative definite, then we can say that x bar is the local maximum solution. In case this gradient of the function at x bar is indefinite, meaning it is not positive definite and not the negative definite, in that case we can say that x is the saddle point or the inflection point. Now, the important question is that when we get a point, say x bar, this x bar is going to be a stationary point. Since we don't know this stationary point is a minimum, maximum or inflection point, at that particular case we need sufficient condition as described here. So, let us see all these conditions together. So, here necessary condition says that a point x bar is a stationary point when the gradient of the function at that point is 0. So, that is the necessary condition, we have to check it. Thereafter, the sufficient condition says that the point which is x bar right now is minimum or maximum or an inflection point if. Now, we are introducing this letter h, which is being referred as Hessian of the matrix. So, this Hessian matrix is positive definite, negative definite, or it can be otherwise. So, based on the Hessian matrix, we can find out whether the stationary point is minimum, maximum or an inflection point. As we know, if we have the function which is a scalar function, when we find the gradient of the function, it is going to be a vector for us. For the same scalar function, when we are going to find gradient of the function, meaning the matrix, so as you can see, a symmetric matrix will come into the picture. Now, the question is that when we are going to get a point, say stationary point x bar, then how would I know that the given matrix is positive definite or negative definite or it is indefinite? So, in order to know this, we have certain conditions. So, the matrix H at a point, say x t, is defined to be a positive definite. So, we can check a condition. So, we have 3 conditions. So, first condition is, let us take any point y in the search space, and if we find this particular quantity as y transpose Hessian y greater than 0, then we can say that the matrix is a positive definite matrix. Similarly, the second condition is, since we already have a Hessian matrix, we can find the eigenvalues. If all the eigenvalues are positive, we can say the matrix is a positive definite matrix. Now, what could be the third condition? This is when we are going to find the principal determinants and all of them are positive, then we can say the matrix is a positive definite matrix. So, we have 3 ways to identify whether the matrix is positive definite or not. Now, how I can find the negative definite? As we know, if we multiply -1 to the Hessian, and if this minus times of the Hessian is coming out to be positive definite, then we can say that it is a negative definite. If it is not positive, not negative, then we can say it is an indefinite matrix. As of now, we have gone through the optimality condition for unconstrained optimization problem. Now, let us move towards the constraint optimization problem. Now, to start with, let us understand the method which is known as method of multiplier. So, we will take first example. Here, let us consider the following nonlinear programming problem. So, NLP. In this case, we want to minimize the function f(x). So, it is again a multivariable function, and this particular objective function is subjected to equality constraint, which is defined as hk of x equals to 0. So, we are taking a simple case right now, and we can have multiple such equality constraints. So, here we are introducing a function called Lagrangian function. In this Lagrange function, we introduce some Lagrange multiplier, say Vk, for each constraint hk. So, meaning that if we have say 5 constraints, then we are going to have 5 Lagrangian multiplier. How we can write this Lagrangian function? So, let us see here. So, the Lagrangian function is made of the variable x1 to xn and the Lagrangian multiplier from v1 to vk. So, we have k number of constraint as of now. So, we have introduced that many Lagrangian multiplier. On the right hand side of the equation, we have the function minus times of, now we are making a summation. Now, this summation means that we are multiplying the Lagrangian multiplier with the equality constraint. What we can see from this particular equation, that we started with the constraint problem where we want to minimize a function subjected to various equality constraints. With the help of Lagrangian method or the Lagrangian multiplier, we have converted this constraint problem into the unconstrained problem. So, the question is, can we use the optimality conditions which we have understood for unconstrained optimization problem? So, the answer is yes. So, in this case, the necessary optimality condition for the Lagrangian function is, so let us find the gradient of this Lagrangian function with respect to x, and we can make it 0. So, this is our necessary optimality condition. So, in this case, when we are going to find the gradient, so we can get gradient of the function minus times of the summation Vk and the gradient of the constraint equal to the 0. So, this is the condition which we know as a necessary optimality condition. Apart from x, we have other variables which is Vk. So, here when we are finding the gradient of the Lagrangian function with respect to the Lagrangian multipliers V, we will get hk of x equals to 0 for all k's. This means that the necessary optimality conditions for a Lagrangian function will be, that is based on the first equation and the second set of equations. So, both of them will be giving us the optimality condition for the given nonlinear programming problem. As of now, we have just taken the equality constraint. Now, let us take the inequality constraint into our problem, and we will see how this Lagrangian or the method of multiplier can be used. Given here is, again we will consider an NLP problem here. We are going to minimize a function, and this function is subjected to the inequality constraint. So, this particular sign greater than equals to 0, that makes the inequality constraint, and we can have various kinds of constraints as well. So, here let us convert this inequality constraint into the equality constraint. So, for this conversion we need slack variables. So, we are going to use non-negative slack variables to convert them. The concept of slack variable we can also understand from the linear programming problem. In that case, the inequality constraints are generally changed into equality constraint with the help of slack variable. Now looking at the equation now, gj of x minus yj square greater than 0 and all these j. So, for every constraint we are putting this slack variable. What is important point here is this yj can take any value, it can be positive or a negative, but yj square will always take a non-negative value. Why? Because the square makes our negative term positive and positive remains positive. So, in this case we are subtracting this slack variable yj square in this particular equation, so that the inequality constraint given here can be converted into the equality constraint. So, let us rewrite this NLP now. In this NLP, we are going to minimize a function, say f(x), and now we are writing as capital Gj, and this is a function of x and a y. And we know x is the set of variables for the given problem and y is the set of slack variable. So, the capital Gj of xy is equal to Gj of x minus yj square equals to 0. So, the same equation which we have written on the top, we are writing here. Since the constraint is converted into the equality constraint, we can use the Lagrangian function. Here the Lagrangian function is, as you can see, it is made of variable set of x, set of y and set of u. On the right hand side we have function f of x minus we have a summation and then we have a Lagrangian multiplier. So, uj is now Lagrangian multiplier for the inequality constraint, and we are writing this gj, which is a function of x and a y. So, we are going to have x, y and u. For this given Lagrangian function, we can find the optimality condition. So, we are going to find the gradient of the function first with respect to x, thereafter with respect to y, thereafter with respect to u, and then we will get set of optimality condition. Now, from this particular equation, we can see that a constraint problem is converted into an unconstrained problem. So, the necessary optimality conditions are, we are finding the gradient of the function L with respect to x and making it equals to 0. That gives me the first set of equation as it is mentioned here, which is gradient of the function minus the summation over all the constraint uj gradient of gj x y. Thereafter, we can have the gradient of the L with respect to u and we are making it equals to 0. Now, since we know the u, as you can see on the Lagrangian function, u is available with the constraint only. So, that is why we are going to get minus gj of xy or minus gj of x plus yj square equals to 0. Now, looking at this condition, we know that this yj square will either take positive value or it will be a non-negative, either it can take 0 value or it will be a positive value, meaning that if you take the whole term on the right hand side, what we can see that we can write this particular condition as gj of x greater than 0 for all the constraint. So, this is the constraint for our problem. The third optimality condition we can get when we will be finding the gradient of the function L with respect to the slack variable y, and then we are making it equals to 0. Now, in this case, the condition which we will get is minus 2 uj yj equals to 0, or we can write uj gj is equals to 0, and this is for all constraints. Now, here the important point is that we have a condition called uj yj equals to 0, meaning that either uj equals to 0 or yj equals to 0. So, let us take the case one by one. If yj equals to 0, meaning that the slack variable is 0. So, if we rewrite our constraint, this says that gj of x minus yj square is equals to 0. So, this current condition says that yj is 0, meaning that gj of x is going to be 0. As and when at any point any of the constraint is equals to 0, those constraints are referred to as active constraints. So, if yj equals to 0, the jth constraint is active at the optimal point. If uj equals to 0, meaning that the jth constraint is inactive, and since it is inactive, it can be ignored because this inactive constraint is not going to change or affect our optimal solution. So, the overall condition uj equals to 0 can be written as gj of x equals to 0. So, as you can see, yj equals to 0 means gj of x equals to 0. So, that is why we are rewriting the equation as we can get it in the terms of gj equals to 0. Now, the above condition will generate the x star, which is we are generally refer this x star for the optimal point or the optimal values. So, we have x star, u star, y star, and that is the optimal solution for the given problem. Now, these are the method of multiplier that is actually helpful to find out the KKT condition. The KKT conditions are referred as Karush-Kuntakar optimality condition for constraint optimization. So, let us look the KKT condition now. Now, here let us consider the NLP as given on the top. Here we are minimizing the function f of x, we have inequality constraints, we have equality constraints, as well as we have variable bounds. So, this is the original problem which we had it earlier. Now, since we have to find the optimality condition, so we know we are going to write the Lagrangian function so that we can convert this constrained optimization problem into unconstrained optimization problem. So, let us see that. So, using the method of Lagrangian multiplier, the inequality constraints can be added to the objective function to make the problem unconstrained. So, here the Lagrangian multiplier, now it is a function of x, u and a v, and we can have a right hand side f of x minus times this summation for the inequality constraint minus the summation for the equality constraint, and uj's, this is the Lagrangian multiplier for gj, and vk, that is the Lagrangian multiplier for equality constraints. So, KKT conditions or Karush-Kuntakar conditions can be obtained by satisfying the first order optimality condition with respect to x, u and v for unconstrained problem. So, this practice we have already done when we have shown the optimality condition for the equality constraint and then thereafter for the inequality constraint. So, if we follow the same procedure, we are going to get the KKT conditions. So, what are those conditions? Let us see that. So, the KKT conditions are, we have the gradient of the function minus, this is the summation uj gradient of the gj minus, then we have a summation vk hk of x equals to hk of x equals to 0. So, this is, you know, we get it corresponding to the optimality condition when we are going to find the gradient with respect to x. Similarly, if we do the same thing, then the equation number 6 is the original constraint, inequality constraint. Equation 7 is the original equality constraint. Equation 8 we get as uj gj equals to 0. So, this condition also we got it, and finally, that all the Lagrangian multiplier corresponding to the inequality constraints, all of them either should be greater than 0 or it can be equal to 0. For the KKT condition, there are certain situations. First is, if a point satisfying the KKT conditions is a likely candidate of the optimum in the constraint optimization problem. So, this statement says that if I get a stationary point, say x bar, and if I find the KKT conditions and suppose all the conditions are satisfied, then this x bar is a likely candidate. Still we cannot say that it is optimum or not, but it is going to be a likely candidate for the optimum solution. However, we can use this KKT condition to say that that if the point is not a KKT point, then it can never be an optimum solution for the given constraint optimization problem. In the bottom, we can see that not all KKT points, the points satisfying the KKT conditions, are optimal. So, let us take a case that since EC techniques, they work on multiple solutions. So, in that case, you will get many feasible solutions. When you get those solutions satisfy the KKT condition, we may find that there will be many solutions which are satisfying the KKT conditions. So, here the statement says that all these solutions are the likely candidate of the optima. However, it is not necessary that all of the solutions are optimum. So, the optimum point will definitely be a KKT point, but all KKT point need not to be an optimal solution for our given problem. So, let us understand those equations one by one. Equation 5, that arises when we are finding the gradient of the Lagrange function with respect to x, make it equals to 0. So, this will give me the optimality condition. Thereafter, as we have understood, the equation 6 and 7, these are our original constraint of the nonlinear programming. So, that is why Gj of x is greater, Gj of x are greater than or equals to 0 and Hk of x equal to 0. Thereafter, we get another condition in equation number 8, that is Uj Gj equals to 0. Now, these conditions generally are referred to as complementary slackness condition. As we have discussed earlier, if the jth inequality constraint is active at a point, meaning that Gj of x is equals to 0, the product Uj Gj is 0. Second is, if inequality constraint is inactive at a point, then Gj of x is greater than 0. So, at that particular point, the Lagrangian multiplier Uj is equal to 0, meaning thereby that in the neighborhood of the point x, the constraint has no effect on the optimum point, and this is what we discussed earlier. If the constraint at a given point is not active, meaning that this constraint is not going to affect our optimum solution. So, in this case, we should make our Lagrangian multiplier Uj should be equals to 0. The another important condition, that is the last condition, we have that in equation 9, all these Uj should be equals to 0. So, for every Lagrangian multiplier corresponding to the inequality constraints should be greater than or equal to 0. Now, here the important point is that when we are going to solve this, the bounds on the variable should also be taken as inequality constraint as given here. So if we are going to consider them, so we are going to have n plus 3j plus k. So total number of KKT condition will be that many. So if we have to say that a point is satisfying the KKT condition, it has to satisfy many equations as given here. Now using this KKT condition, we have two theorems. First is called KKT necessary theorem. So let us look at this particular theorem first. For the NLP, the function f, so this is our objective function, g means our constraint, inequality constraint, and h is our equality constraint. All of them are differentiable function, and x bar is a feasible solution to the given NLP. So let us find out what are the solutions which are active. So here let I is equals to all those constraints which are active at a point, say x star. So that denotes that the set of active constraints are copied to I. Furthermore, when we are finding the gradient of the inequality constraint which are active and the gradient of the equality constraints, and they are linearly independent. So this condition has to be satisfied. In that case, if x star is an optimal solution to NLP, then there exists u star and v star such that x star u star v star satisfies KKT condition. So meaning that if we are going to have active constraints, active inequality constraints, and then we have equality constraints, the functions are differentiable, these gradient of the constraints are linearly dependent. So for a given point, say x star, there will be other set of point u star and v star. So we know u and v are our Lagrangian multiplier for equality and inequality constraints. So those point will be satisfying all the KKT condition. Based on that, here as we know, the point which is satisfying KKT condition is a likely candidate for the optimum solution. Then in which situation this KKT point can become the optimal point. So in that case, we have another condition called KKT sufficient theorem. Let us look into that. The KKT sufficient theorem says that let the objective function be convex. How we can find convex? We can find the Hessian of this function, and if it is positive definite, we can say it is a convex. We will discuss more on it. So let us assume that the objective function be convex, inequality constraint Gj of x be all concave, and equality constraints are linear. If there exists a solution, say x star, u star, v star satisfying the KKT condition, we can say that x star is an optimum solution to the NLP problem. With the help of necessity theorem, we can find a set of x star, u star and v star that are satisfying all KKT conditions. But when we are solving a problem in which the objective function is convex, the inequality constraints are concave and equality constraints are linear, then we can say that x star, u star, v star are the optimum solution for the given problem. Now the question is how we can find a function is convex or a concave. So here we will just have an introduction of convexity. So the function f of x is defined as a convex function if for any 2 points, say x1 and x2 in the search space, and the lambda is lying between say 0 and a 1, and this condition satisfies, which says that function value at lambda x1 plus 1 minus lambda times of x2 is smaller than equal to lambda times of f of x1 plus 1 minus lambda times of f of x2. So, this particular relation is valid for single variable function as well as for multivariable function. Similarly, we can find the Hessian of the function and we can check whether this Hessian matrix is positive definite or not. So, as we have understood earlier that if we find the Hessian, in that case the first condition says that we are going to we have any point say y in the search space. If the condition given here is satisfied, that says that y transpose Hessian y greater than 0, then definitely the matrix is positive definite. Second condition is all eigenvalues are positive, then the matrix is positive definite. Similarly, when all presimple determinants are positive, then the matrix is positive definite. So, while satisfying any of these conditions, we can say the matrix is positive definite. Eventually, we can say the function is convex. Then what will happen to the concave function? So, here we can do simple simplification, that we will take say g j of x as minus times of g j of x. We can find the gradient of the function of g j of x, and if this is coming out to be positive definite, then we can say the constraint is concave. So, that will help us to identify the function is concave, convex or a concave. So, with this introduction, that we have understood the optimality condition for unconstrained optimization as well as the optimality condition for the constrained optimization. Mainly those conditions are referred to as KKT condition. We have come to the closure of this session. So, in this particular session, we have gone through the first understand the constrained optimization formulation, in which the objective function was subjected to inequality constraint and the equality constraint. Thereafter, we have understood the constrained optimization problem with the help of graphical example, where we have continuous search space, we can have discontinuous search space. Thereafter, we have gone through the optimality condition for unconstrained problem. Now, the unconstrained problem, we are going to find a stationary point. So, we have necessary optimality condition, we have sufficient optimality condition. Thereafter, for constrained optimization, we have gone through the method of multipliers. So, these method of multiplier will help us to find out various conditions. So, finding gradient of the Lagrangian function. So, what we understood from this method, that a constrained problem can be converted into the unconstrained problem, and the optimality condition of the unconstrained problem, we can use it here to find whether the point is optimal or not. Thereafter, we have gone through the KKT condition for constrained optimization, and at the last we discuss the convexity, since it will be helpful to find out whether the function is convex or not. With this background of the optimality condition on constrained and unconstrained problem, I conclude this session. Thank you.